Today we're going to talk about a topic called chemical equilibrium. And chemical equilibrium is when a reaction is happening both forwards and backwards at the same rate. This could be written as A plus B reacts to C plus D, whilst C plus D reacts to A plus B. There are some conditions, however, that must apply for this equilibrium to actually exist. And one of them is that it must be a closed system. So if gases were involved in the reaction, they wouldn't disappear, they would stay and react. And also both products and reactants must be present at all times. Since these reactions happen at the same rate, we know that their rate equations must be equal to each other. And rewriting these equations, we get the equilibrium expression, which says that the equilibrium constant is equal to the products divided by the reactants, and is also equal to Q only at equilibrium. Q describes the ratio between products and reactants, and Q can differ if you were to increase the concentration of products, but Q will only be equal to K at equilibrium. K is the equilibrium constant describing the ratio between the concentration of products and the concentration of reactants at equilibrium, and K is the result of two constants who are each dependent on the temperature, so the equilibrium constant K must also be dependent on the temperature. So K is only given for a certain temperature. The specific equilibrium expression for this reaction would be C to the power of C times D to the power of D divided by A to the power of A times B to the power of B. Now, these concentrations are put to the power of their coefficients, which can only be used if the reaction is an elementary reaction with no reaction mechanism. And if you were to increase the concentration of D, for example, a guy called Henri Louis Le Chatelier formed a principle that describes what would happen. He said, if one or more factors that affect the equilibrium is changed, the position of the equilibrium shifts in the direction that opposes the change, meaning that if you were to increase the concentration of D, the equilibrium would use some of that to form more reactants to reduce the change. Now, in our experiment, we experimented with the equilibrium. Iron 3 ions plus thiocyanate ions reacted to iron 3 thiocyanate ions. So this was all in an aqueous solution, so we didn't need a closed system. The closed system was in the liquid. And it was quite fast reactions. As soon as we mixed iron 3 ions and thiocyanate ions, we got this red liquid. And the equilibrium expression for this specific equilibrium would be the concentration of iron 3 thiocyanate divided by iron 3 ions times the concentration of thiocyanate ions. And in this equilibrium experiment, we added a stress, so we changed some factors in the equilibrium in different ways. We had 4 test tubes. In the first, we had a small sample of the equilibrium, and then we increased the concentrations of iron 3 ions. So using Le Chatelier's principle, the equilibrium would shift towards the product side, meaning that it would turn more dark red as iron 3 thiocyanate is the contributor of the red color, which it also did. The second, we did almost the same thing. We increased the thiocyanate concentration by adding more of it, and the same thing happened as they're both reactants, so it turned more dark. Before doing the third experiment, or experimenting in the third test tube, we added ascorbic acid to iron 3 ion in the test tube called 1A. And this turned iron 3 ions into iron 2 ions, slightly losing its red color, meaning, no, it's yellow color, sorry. Iron 3 ions have this yellow color, and as soon as you reduce them into iron 2 ions, they lose that yellow color, so it turns slightly yellow and more colorless. And when we added this ascorbic acid into test tube 3, it decreased the concentration of iron 3 ions, meaning that more product was used to form more iron 3 ions. We added a bit much, meaning that it turned all the product into reactants, so it lost the entire color, but the principle is still the same. In test tube 4, we decreased the thiocyanate concentration by first taking some potassium thiocyanate and adding some silver nitrate to it to see that the silver 1 thiocyanate formed a white precipitate, a solid salt, and an insoluble salt, and also the potassium nitrate doesn't really matter, it's just spectate ions. So by adding silver nitrate into test tube number 4, we decreased the concentration of thiocyanate ions, meaning that more product was used to form reactants. This turned it slightly less red. It can be compared to test tube 7 that hasn't been touched with. In test tubes 5 and 6, we first increased the temperature in test tube 5, and then we decreased the temperature in test tube 6. In test tube 5, the reaction, it became slightly less red, and in test tube 6 it became slightly more red, slightly darker red. By this experiment, we can see which reaction is the exothermic and which is the endothermic, because if you increase temperature, the equilibrium will shift in the same direction as the endothermic reaction, because it will try to reduce the change by using more heat. So when we added heat, it shifted to the left, meaning that the reaction going to the left must be the endothermic reaction, and when we decreased it, it moved to the right, meaning that the reaction going towards the right must be the exothermic reaction producing heat. And for the last part of this experiment, we had a solution of potassium permanganate, and we had a small part of our equilibrium solution. And what we did was we doubled the volume of these by simply just adding water, meaning that we decreased the concentration largely. The purple are the potassium permanganate, and when we increased the volume, when you look from the left, it becomes slightly less purple, it becomes slightly more faded when we look from the side, because we can see the same amount of molecules spread out over a larger area. But when you look at it from above, it has the exact same color, because we're looking at the exact same amount of molecules on the exact same area, the same surface area. But in our equilibrium mixture, it still looks less red from the side, but it also looks less red from above. And this can be explained mathematically. When we double up the concentration, we'll cut our concentrations of products and reactants in half. So in this equilibrium expression, we divided the iron 3 thiocyanate concentration in half, and also the two reactants. So we can see in this expression that on the top of the fraction we halved the value, but on the bottom we halve the value twice, meaning that we have 1/4 of what we started with. So it's now out of balance. Q is not equal to K. So to bring Q back to K and bring the reaction back to equilibrium, more product was used to form more reactants, meaning that it becomes slightly less red because there's not as much iron 3 thiocyanate left. And I believe this was all.